Welcome, students. This is a quick summary of combinatorial probability. In the last video, we studied combinatorics. In combinatorics, we were interested in finding the number of ways we can perform certain operations. However, more commonly, in a lot of cases, we are more interested in finding probability of certain event. For instance, poker player would rather be interested in finding probability of a flash, of him drawing a flash, rather than counting the total number of ways he can draw a flash. So transition from combinatorics to combinatorial probability is rather straightforward. If there are total n number of ways we can perform certain operation, let's call this number as small n, and out of those n number of ways we can perform that operation, let's say m satisfy our stated condition, then probability of our event A is equal to m over n. So n is the total number of outcomes and m is the total number of desirable outcomes. Now let's take a look at a couple of problems. So there is an urn. There are chips numbered 1 through 8 in it. Now, let's calculate the probability of the following event. Let's call it event A. Largest chip. Largest chip is 5. When we draw a sample of 3 chips from our urn. So we draw 3 chips. What's the probability that the largest chip in our sample is 5? We draw these chips without replacement, and the order doesn't matter. So drawing chip 1 to 3 is the same as drawing chip 3 to 1. All right. Now, first of all, let's take a look at an event largest chip is 5. We can define it as the intersection of the following two events. So first, we have to have a chip numbered 5 in our sample, right? So first we should have, let's call it some event B. Chip number 5 is drawn. Second, this chip number 5 should be largest in our sample, meaning that all other chips, the 2 other chips that are drawn, are going to be drawn from a subset of a sample space numbered from 1 to 4. So second event is 2 out of 1, 2, 3, 4 are drawn. The total number of ways we can perform B is 1 choose 1, since there is only a single chip numbered 5 in our urn here. Number of ways we can perform C is 4 choose 2. So we are choosing 2 chips out of these 4 here. Now, by multiplication rule, the total number of ways we can perform A is then equal to the product 1 choose 1 multiplied by 4 choose 2. And finally, the total number of ways we can choose 3 chips out of our 8 here is given by 8 choose 3. So probability of A is then defined as the following ratio here. Now, on to our next example. We have an urn. There are n chips, n blue chips numbered 1 through n. So these are blue chips. N chips numbered 1 through n. These are black. And n chips numbered 1 through n. These are red. Okay, so we are drawing two chips without replacement. Now, what is the probability that the two chips are drawn are either same number? They either have same number on them or same color. So we're looking for probability of drawing same number, two same number chips, or two chips of the same color. Let's call this as an event A. Then event A can be represented as the union of the following two events. Event of drawing same number or event of drawing same color. Let's call this as event B and event C. Now, this is union of B and C, which can be expressed as the sum of probability of B plus probability of C. Since B and C are mutually exclusive, since, for instance, you cannot draw two red chips numbered 5, since there is only a single chip, red chip numbered 5 in our urn here. Now, let's find probability that we are drawing two chips that have the same number. So probability of event B might be expressed as the probability of the following union of events. So either we draw two ones, or we draw two twos, or two threes, and so on, or two n's. So two chips with number n on them. Now, all these are mutually exclusive, so we can't have an event of drawing two chips numbered 1 and two chips numbered 2 at the same time, obviously. So this can be expressed as the sum of this. And so on. Now let's take a look at an event of drawing two chips with number 1 of them. So there are 3 choose 2 number of ways to perform that. So we have 3 colors in our urn: black, blue, and red. So there are 3 choose 2 number of ways to perform an operation of drawing two chips numbered 1. Total number of, by the way, all these are going to have a same denominator. Total number of ways we can draw two chips out of our urn here that has 3n chips is given as 3n choose 2. Now, by the similar argument, the total number of ways we can draw two chips numbered 2 is 3 choose 2. So we are choosing 2 colors for our chips numbered 2, and so on. And 3 choose 2 number of ways to perform an operation of having 2 chips numbered n. So this sum here is equal to n multiplied by 3 choose 2 divided by 3n over 2. I mean 3n choose 2. Now let's find probability of drawing two chips that have the same color. So this can be expressed as probability of having two blue chips or two black chips or two red chips. Now, all these are mutually exclusive. We can't have an event where we draw two blue and two black chips at the same time. So we express it as the following sum where we have two blue plus probability of drawing two black plus probability of drawing two red chips. Now, let's find probability of drawing two blue chips. So there are n blue chips in our urn here. So total number of ways we can perform operation of drawing two blue chips is given as n choose 2 then. Total number of ways we can perform an operation of drawing two chips out of 3n is given as 3n choose 2. Now these all are going to have the same denominator plus probability of drawing two black chips. This is black, this is blue. So let's say probability of drawing two blue chips is given as n choose 2 plus probability of drawing two red chips is also n choose 2. So this is 3 multiplied by n choose 2 over 3n choose 2. Choose 2. Now we're looking for probability of A, which is going to be equal to the sum of these two fractions. All right, now let's take a look at one more example. Let's suppose that we select k people from general population. Now let's find probability that at least two of those k people have the same birthday. This is known as a birthday problem. So we're looking for probability that probability of A, at least two of those k people having the same birthday. Now, we can look at this problem as a problem where we work with ordered sequences. Since, let's say, we have Aigerim, Big Sultan, and so on. So let's say number 1 will correspond to the birthday on 1st of January. And let's say number 4 is on 4th of January and so on. Now drawing a sequence 1, 4 is different from drawing sequence that starts from 4 and follows by 1, since that sequence will correspond to Aigerim being born on 1st of January and Big Sultan being born on 1st of January, as opposed to Aigerim being born on 1st and Big Sultan being born on 4th. So total number of such sequences is then equal to 365 to the power of k. So let's say we have Aigerim, Big Sultan, and so on. So there are k people. 365 choices for Aigerim, 365 choices of birthday for Big Sultan, and so on. So there are k people, and total number of ways of choosing those k people from general population is 365 to the power of k. Now, let's calculate the number of sequences we have in the following event where at least two have the same birthday. So probability of A then might be expressed as number of sequences in A over 365 to the power of k. Now, calculating the number of sequences that we have in A is much more harder than calculating the number of sequences that we have in A complement. Now, we can divide our sample space into the following two categories. So first category is when at least two have the same birthday. The complement of this is going to be all those k people having different birthdays. All k have different birthdays. Now, those two events, they partition our sample space. So probability of A then might be expressed as 1 minus number of sequences in A complement. So number of sequences where all k have different birthdays. K different birthdays. Right, over 365 to the power of k. Now calculating that is much more easier. 1 minus this is simply permutation of length k out of 365 elements. So we have 365 choices for a first person multiplied by 364 choices for the second person, since we cannot already use the birthday that we used for the first person, and so on. Multiplied by 365 minus k plus 1. Divided by 365 to the power of k. Now, if we put in some numbers here, we get quite an interesting results that can be seen in the following table. So it turns out to get a probability of 50% of two people having the same birthday, we are required to have only 23 people from general population. So if we have 23 people in a room, then probability that at least two of them have the same birthday is equal to 50%. Right? So you can see other interesting results here. So we only need 70 people to get 99.9% of at least two people having the same birthday. All right, now let's take a look at one more example. Now let's calculate some probabilities that are related to poker hands. Let's start by, so we'll be working with the standard 52 cards poker deck. First, let's calculate the probability of a full house. Full house consists of 3 cards of one denomination and 2 of another. So for instance, we'll have 3 sevens, let's say 7 of hearts, 7 of diamonds, 7 of clubs, and 7 of spades. I mean, we don't need 7 of spades, right? And 2 cards of another denomination, let's say couple of kings. Let's say king of spades, and king of hearts. So this is one example of a full house. Let's calculate the probability of a full house. So total number of ways to choose 5 cards out of 52. So standard poker hand, starting poker hand is 5 cards. So this is 52, choose 5. That we have in denominator. Now let's split that into the following two operations. So first, an operation of choosing 3 cards of the same denomination. So first, let's choose denomination for those 3 cards. So there are 13 denominations. First, we choose denomination for those 3. So 13, choose 1. Then we have to choose suits for those 3 cards. There are 4 suits, and we choose 3 suits out of those 4 for our first 3 cards. Next, we are going to choose a denomination for the left 2 cards here of the same denomination. This is 12, choose 1, since we've already used one denomination here. Multiplied by the choice of suits for those 2. There are 4 suits, so 4, choose 2. Next, let's calculate probability of one pair. So probability of one pair. Now, one pair is a case when we have 2 cards of the same denomination. Let's say a couple of 7s. And the left 3 cards are all going to be of different denominations. So let's say queen, king, and let's say 2. Now that probability is then equal to 52, choose 5. This is our denominator. First, let's have an operation of a choice for the denomination of the first 2 cards that have the same denomination. So operation of a choice of a denomination for our pair. So there are 13 denominations, 13, choose 1. Next, we are going to choose a suit for our 2 cards here of the same denomination, which is 4, choose 2. Multiplied, then we have to choose a denomination for cards that have no pair. This is 12, choose 1. Since we've already used one here, we are going to choose a suit for this one. This is 4, choose 1. Multiplied by, next we are going to choose denomination for this 4th card here, which is 11, choose 1, since we already used one denomination here, one denomination there, multiplied by 4, choose 1. This is a choice of a suit for a 4th card, multiplied by a choice of a denomination for our last card here. This is 10, choose 1, multiplied by 4, choose 1, which is a choice of a suit for the last card. So this can be expressed as 13, choose 1, multiplied by 12, choose 1, multiplied by 11, choose 1, multiplied by 10, choose 1, multiplied by 4, choose 2, multiplied by 4, choose 1 to the power of 3. 4, choose 1 to the power of 3, divided by 52, choose 5. Okay, great. Now let's calculate the probability of a straight. So a straight is a case when we have 5 cards that are consecutive in denominations, but not all in the same suit. So for instance, we'll have 2, 3, 4, 5, and 6. However, all of them cannot be of the same suit. We cannot have all of them being hearts. So one of those should, at least one of those should differ in terms of suits. So one of this is going to be, let's say, spades. Now, denominator is always the same, 52, choose 5. Now let's find our numerator. If we order all our cards, all our denominations in a poker deck, there are 13 cards. 2, 3, 4, 5, 6, 7, 8, 9, 10. Jacks, queens, kings, and ace. One thing to notice is that ace might be considered as high or low. So ace, 2, 3, 4, and 5, this is a straight, and so is 10, jacks, queens, kings, and ace. This is also straight. Here ace is counted as a low, and here ace is counted as a high. So there are 10 starting points for our straight. So our straight either can start from ace, go up to 5, it can start from 2, go up to 6, and so on. It can start from 3, from 4, from 5, from 6, from 7, from 8, from 9, and last it can start from 10. There is no straight starting from jacks. So jacks, queens, kings, ace, and 2 is not a straight. So there are 10 ways to choose a starting denomination for our straight. So let's add this as our operation. 10 multiplied by. Now, since we've chosen our starting point for straight, now let's choose the suits for those. Now let's approach our problem in the following way. Now let's assume that, let's start by assuming that all these 5 cards having the same suit is fine for now. So we have to choose suits for those 5 cards. This is going to be 4, choose 1 to the power of 5. However, if we leave it as it is, number of sequences that we have considered here is going to include a case when we have all of our 5 cards having the same suit, which is a straight flush, which is slightly different from a straight. Now let's exclude those. Let's exclude those cases. Let's exclude the cases when we have 5 cards in consecutive order, all of them having the same suit. This is equal to 10. First we are going to calculate the number of ways we can perform an operation of our starting card for our straight flush, multiplied by the total number of ways we can choose a suit for those 5 cards. There are 4 suits, so 4 choose 1, or this is equal to 40. All right, so the probability of a straight is calculated in the following manner. Now, using a similar way approach, we've calculated probabilities of a straight, 1 pair, and full house. We can calculate other probabilities for various poker hands, and they are given in a nice table over there. All right, and now this is going to conclude our video on combinatorial probability. Next chapter is a chapter on random variables.